All right, so lesson 2.3. We're going to get a little bit further into derivatives. We have some certain rules here, our product and quotient rule that we're going to get into shortly. But before we do that, kick off here from the last time. Remember, we have our power rule, which says we're just going to take the exponent that times anything in front to make this a 6. We subtract 1 so that our new exponent is now 2. So derivative of 2x to the third goes to 6x squared. So first one, product rule. So if we have two functions times each other, to do the derivative, we're going to do the first function times derivative of the second plus the second times derivative of the first. So essentially, derivative of the one times the other and then adding the opposite way. So if we're doing one like here, so here, a little more obvious that, okay, these are two different functions. So we have our first one and our second one. So whether we do derivative of the first times the second or the first times derivative of the second, doesn't matter. We just do the opposite the next time. So if I do the derivative of the first one here, derivative of 3x would go to 3 minus, the 2 would come down to make this 4x. So because I derivative the first one, we just write the second then, 5 plus 4x. Plus, so now the first one stays the same. Derivative of the second, derivative of 5 would be gone, and derivative of 4x would be 4. So first one we'd have to FOIL. 3 and 5 would make 15. 3 and 4x would be plus 12x. Negative 4x and 5 would be minus 20x. Negative 4x, positive 4x would be a minus 16x squared. Here we just got to distribute the 4 in. So plus through 12x minus 8x squared. So like terms get put together. 15 is the only constant. 12x and 12x would be 24x minus 20 leaves us with a plus 4x. And negative 16x squared and negative 8x squared would be minus 24x squared. And that's our answer there. Now here, it's a little less obvious as to what the two different equations are. But sine, the trig function sine is considered 1. So that means our 3x squared is the other one. So derivative of the first, 2 would come down. This would become 6x sine of x plus 3x squared. Derivative of sine is cosine. And really that's as far as we could take it. We could pull a 3x out. This would be good. Okay. Now, the other side of this is now if they're divided, we're going to do the quotient rule. Here it's very specific, so it has to be the bottom times derivative of the top minus the top times derivative of the bottom all over the bottom squared. So g of x is the bottom, f of x is the top. So bottom, top, top, bottom. Bottom, derivative of the top, top, derivative of the bottom, bottom squared. Okay? So here, so derivative of the top would go 5x becomes a 5. The 2 would be gone. So now times the bottom of x squared plus 1. Minus derivative of the bottom, which x squared would go to 2x. 1 would go nowhere, go to 0. Times the top, which is 5x minus 2. All over the bottom squared. So x squared plus 1 quantity squared. So if we distribute our top here, we'd have 5x squared plus 5 minus 2x and 5x would be minus 10x squared. Minus 2x times 2 would be a plus 4x over x squared plus 1 squared, which we could simplify this down to, so 5x and negative 10 would be negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. Now, this one doesn't factor out, at least not to an x squared plus 1 anyway. So this is really as far as we need to take it. There's nothing else that's going to reduce. So we're going to leave it there. Now, sometimes we do have to rewrite them a little bit before we do the derivative. And that's just to make it a little nicer with doing the derivative. Because I always like, if we left it how it is, this 1 over x would need the difference quotient, and then you do difference quotient again, and it gets into a big mess. So, how we're going to do this is this. Mainly, it's the issue of fraction inside of a fraction here. And so to get rid of that fraction inside of a fraction, we're going to take the top and the bottom times an x. So our equation goes to 3x minus 1, because you'd have x over x, which would go to a 1. On the bottom, x squared plus 5x. Now it's just like the one we did up here. So much nicer to do quotient rule with. So derivative of the top would be 3 times the bottom of x squared plus 5x. Minus. Derivative of the bottom would go to 2x plus 5 times our top of 3x minus 1. And it'd all be over x squared plus 5x squared. So top here we can distribute in. Bottom's still going to be x squared plus 5x. Nothing's going to change there. Squared. We'd have 3x squared plus 15x. Here we're going to FOIL and subtract it. So 2x and 3x would make a minus 6x squared. 2x and 1 would be a plus 2x. 5 and 3x would be 15x, but it's be minus 15x. 5 and 1 would be a minus 5 over minus, and so plus 5. So, and I should have wrote this on the last one, but f prime of x. Remember, f prime means derivative, so it's going to be this. So our x squared plus 5x squared on the bottom. Top, we have a 3x squared and a minus 6x squared to make minus 3x squared. 15x minus 15x are going to cancel. So we're left with 2x. And the only other thing is plus 5. And again, that's as far as we can take that one. So we're going to leave it as such. Now, constant multiple rule applies to things like this too. Let me focus in on this here part. So what this is really saying is we could pull that 1/6 out front, so all we got to do is just derivative the inside. So 1/6 x squared would go to 2x, 3x would just go to a 3, and then we could distribute it back in, and then reduce, which would leave us with 1/3 x plus 1/2. So if there's just a number on the bottom, we don't necessarily need to do the quotient rule. I mean, you could, and it would come out to be the same thing, but you can treat that as a multiple and then just do the regular derivative. Now, as far as the other trig functions go, derivative of tangent goes to secant squared. Cotangent goes to a negative cosecant squared. Secant goes to secant x tangent x. Cosecant goes to a negative cosecant x tangent cotangent x. So, derivative of x minus tan of x. So, y prime equals, we have a minus separating the two, so we don't have to do a rule. We can just do the straight up derivative. So, x would go to 1 minus tangent would go to secant squared of x. And we put the squared there so we know it's going with the trig function and not the x. So that's just why it's secant squared x. Okay. So here though, here there are times. So this one will need the product rule. So y prime would equal, so derivative of the first would be 1 times the second secant of x minus x times derivative of secant goes to secant x tangent x. It would be plus, and we don't need to divide. I'm thinking quotient rule. So if we simplify this down, y prime would equal secant of x plus x secant x tangent x. Now we could pull a secant of x out. Either way works. But this is really as far as we need to take this one. Now, sometimes you can get different forms of a derivative. So what we're going to end up doing here is find the derivative of each side, and we're going to show that they're both going to be the same thing in the end. So 1 minus cosine x over sine x. Now, that is a, we got a fraction there, so two functions divided, quotient rule. So derivative of the top, derivative of 1 is 0, so that's gone. Derivative of cosine would go to a negative sign, so the negatives would cancel, and we would just have sine of x. Times the bottom, which is another sine of x. Minus. So derivative of the bottom would be a cosine x times the top of 1 minus cosine of x all over the bottom squared. So sine squared x. Now, if we simplify this, we have, so y prime. So because there was a y, we're doing y prime. But sine and sine, we could write this as sine squared of x minus cosine. We could distribute in, and we have minus cosine of x plus cosine, squared of x all over sine squared x. Now, there is a trig function, I'm going to write it up here, where it says sine squared plus cosine squared equals 1. It's a Pythagorean identity. So we have a sine squared and a cosine squared that happen to be plus, even though the cosine's in the middle, but those parts could add together, and we end up being 1 minus cosine of x over sine squared of x. And we're going to leave it at that point right now. But what I did is I took this sine squared and this cosine squared. Because they're both positive, they're technically both positive here. So they're technically added together, and so we can replace them with a 1. So I put a 1 in, and then our minus cosine that was left is where that came from. Now, on the second one there, I'm going to write this y equals cosecant x minus cotangent x. So we know what we're working with. And I'm going to slide this up a little bit. All right, so using that theorem 2.9 where it shows what each one is, when we go about to do our derivative, now here are two functions subtracted, so they're separated by minus, so we don't have to do product rule here. So derivative of cosecant would go to a negative cosecant x cotangent x minus cotangent, which would go to a negative, so make that a plus, cosecant squared of x. Now, what I'm going to do is I'm going to come back to this up here. And I'm going to show if we keep going with this, we're going to get this here. I just ran out of space. So I'm going to keep going with this one here. So I could separate that one and make it y prime equals 1 over sine squared x minus cosine x over sine squared of x. Which I'm going to split again, 1 over sine squared of x minus 1 over sine x times cosine x over sine x. And here's why. So 1 over sine squared, well, 1 over sine is, if you think back to the reciprocal identities, 1 over sine is cosecant. So if it's squared, this is going to end up being cosecant squared of x. Minus 1 over sine, cosecant. Cosine over sine, cotangent. All those are reciprocal identities, although this is one of the quotient identities. But if you think about it, we have a minus cosecant cotangent, minus cosecant cotangent, plus cosecant squared, cosecant squared. So we're good. Last little bit here. So we can get into higher order derivatives. So we can do the derivative of a derivative of a derivative and keep going until we have nothing left. So first derivative is a single prime, second derivative double prime, third prime. After that, then they just use the number. So the fourth derivative would be y with a little 4 in parentheses. Anything past that, we just put the little number in parentheses. So where this helps is, so last time we found out that position, if we do the derivative of that equation, we get the velocity equation. Well, if we do derivative of the velocity, then we get the acceleration. So the second derivative of position is velocity, or is there acceleration, sorry. So because the moon has no atmosphere, there is no air resistance, allowing a hammer and feather to drop at the same rate. Really kind of cool. The position function of each object is given by s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. What's the ratio of Earth's gravity to the moon? So if this is our position, so s prime of t is going to be our velocity function. So if we do the first derivative, the 2 would come down and this would become a minus, and 0.81 times 2 is a negative 1.62 t, and the 2 would go to 0, so it'd be gone. So we're going to do the second one of t. So in other words, the first derivative of velocity to get our acceleration. So derivative of negative 1.62 t is just going to be negative 1.62. I believe this is in meters. Yep, meters per second squared. So it's wanting to know what's the ratio of Earth's gravity to the moon. Well, Earth's gravity is going to be negative 9.8 meters per second to a ratio of negative 1.62 meters per second. So in other words, we're going to take negative 9.8 and divide by negative 1.62. So negative 9.8 divide negative 1.62. It's going to be about 6.05 times. So Earth's going to be about a little over 6 times what the moon is on gravity. Which is why if you ever watch videos of the space people or the space people. Wow. The astronaut, the moon landings is where I'm going with this. If you ever see picture or video of the moon landings, you see when they walk, they kind of bounce. Well, because they have less gravity, they kind of bounce instead of just a flat walk across. I think it's also something to do with moving in the suits, but I could be wrong. Anyways, that is it for the calculus lesson. Let me know if you have any questions. Otherwise, next time, we'll talk to you later.